Hey, mathletes, welcome back. What we're going to look at here is what I'm going to call the tangent problem part two. Remember, we talked about the tangent problem part one way back in lesson one, which was about using the slopes of secant lines to find the slope of the tangent line. And since that time, your next few lessons, you've been looking at all these limits, one-sided limits, limits in general, okay? And maybe you've been asking yourself, well, why have I been, again, what's with these crazy limits, okay? And that's what we're gonna figure out right now. Why are we figuring out those crazy limits? If we can go all the way back to lesson one, what we talked about was the tangent problem, is we wanna know the instantaneous rate of change at any given moment on a curve. And so remember, what we did was we said, there's this green point here, and I've got the secant line drawn. And what we did was we said, as the slopes of the secant line change, as we move that green point closer to the blue point, the slopes of the secant line will approach the slope of the tangent line. And if I can get it, it's horizontal, there it is. So the slopes of the secant lines approach the slope of the tangent line. And that gives us the instantaneous rate of change at that moment, right? And that's the big goal for this whole first half of calculus, is to find that instantaneous rate of change. Now, you didn't know it, friends, but as you've been doing the limit questions in your homework the last few lessons, that's what you've been doing. You've been finding instantaneous rates of change. I'm going to show you that now. Okay, so you're going to see where these crazy kind of limit things that you've been doing, right? They kind of look crazy. You're like, where are these things coming from? You're about to see that now. Okay, this is very conceptual. I'm not going to lie to you. You might have to watch this a couple times. All right, here's what we're going to do, friends. We've got our function, and I'm going to call this function f at x, right? Keep it simple. Call it f at x. And there's 2 points on here. We've got the green point and the blue point. All right, well, I'm going to call the green point up here. Well, I'm going to label it. I'm going to label it x, comma, y. But I want to be a little bit smart about the y. I'm going to write that in a different way. The other way to write that, friends, is to say that's x, comma, the function at x, right? That's that. Okay, so those two things are the same. Okay, so that's what I'm going to call that green point up there. X, comma, f at x. And I just, again, need you to remember that f at x really means our output at the point x. Okay. This blue guy down here, I'm going to label it as a, comma, f at a. Okay, and probably way back in history, they used a alpha beginning point, right? We're going to move towards that beginning point. Hard to say. Okay, now what we're going to do is I'm going to move this green point again towards the blue point. And I'm going to think about the slopes as I do that. So let's just think about the slope for a moment. How do I find slope? Well, slope is change in y, right? So delta y, so f at x minus f at a over change in x, so delta x, x minus a. Okay, that's your slope of your secant line. It's the average rate of change between those 2 points. But friends, what happens as we drag that green point closer to the blue point? What happens as x goes towards a? What happens as x approaches a? The slopes of the secant lines approach the slope of the tangent line. Another way to say we're approaching another point is we're saying the limit. So here's what we have. This is the limit as x is going towards a. Just like that. This, friends, is one of our instantaneous rates of change formulas. Okay, I believe the textbook calls this one method one. This is actually the Newtonian method after some famous smart guy I heard of once called Newton. This is how he figured out the instantaneous rate of change. Okay, so there's one way to find the instantaneous rate of change. The limit as x approaches a point of the function as we move closer. Now, the problem is, friends, not much of a problem, but we got to go back in history for a minute here, is way back when they were first figuring out all these problems about 600-700 years ago. We had Newton over in England. I think he was at Cambridge figuring this stuff out. Well, unfortunately, friends, back then, you got to think about how difficult it was to do any work and to share it, is that there was some other brilliant people over in Germany working on the exact same problem at the exact same time. And you got to think, they can't watch a video and send it on a cell phone as a text like we are right now, right? The death of distance, that's called. So you got someone else thinking of the same problem, but far away. And so here's what this other person comes up with. This other brilliant person, Leibniz was his name, or Leibniz. I can never get the pronunciation correct. Forgive me if you can speak German. You might be getting mad at me right now. Here's what this brilliant person said. They said, okay, look, we're going to start at A, and we're going to still call this point A, F at A. But now I've got this other point over here, and I want to compare it to A. So instead of just making it a random point, X, F at X, what they say is I've moved some distance over, and that distance over I'm going to call H. Okay? I've moved some distance over horizontally. I'm going to call that H. So it doesn't matter if I've moved it to the left or to the right. I'm going to just call it A plus H. I'm some distance over. And in this case, if I've moved to the left, H would be a negative value. So my new point, the X coordinate, is A plus H. The Y coordinate then would be the function at that moment. And so they call it A plus H, F at A plus H. Okay, so how is this person thinking of slope? Well, this person's thinking of slope like this. What they're saying is the slope is the change in y. So they say f at a plus h minus f at a, that's the change in y values, over the change in x values. So a plus h minus a. Well, look at what happens in the denominator there. We can cancel the a's and we're just left with an h. Okay, so what we have right there, that's the slope of the secant lines. But I don't want the slope of the secant lines. I want the slope of the tangent line. So what we're again going to do is we're going to pull that green point closer to the blue point. Well, what's happening? As we move this point over and our secant lines are changing, I want you to think to yourself, what's happening to that value of h? As we move it closer, what's happening to h? Is h getting bigger or is h getting smaller? Is h getting bigger? Is h getting smaller? Well, as we move towards that point A, h is getting smaller. How small is h getting as we drag it closer? How small? It's getting so small, we might as well call it 0. So this is the limit. This is the limit. M is the limit. As h approaches 0, of f at a plus h minus f at a over h. And what we have right here, I believe this is what the textbook calls method number 2 for some reason. Maybe because they think that Leibniz found it second. I don't know. But what we should really be calling it, friends, is the first principles of calculus. And with a name like that, it's mighty, mighty important. So we've got 2 ways, friends, that we are going to write the slope using limits. We've got that one. We've got this one. They both do the same job. It was just that we had 2 geniuses working on a problem at the same time in different parts of the world. They both give us the instantaneous rate of change at an exact moment, and that's our goal. And now I also forgot to write the limit there because I was talking as x approaches a. And now, friends, you're starting to see where all these limits are that you've been working with. Where have they all been coming from? This is where they've been coming from. So, friends, when you've been finding limits, you've been finding the instantaneous rate of change. And that is an incredibly important thing. We're going to use it for important applications to say how fast is my money growing, how fast is this bacteria growing, and other things we're going to do is we're going to graph some really complicated functions without a graphing calculator, and we're going to want to know the slopes all over the place of some crazy curves. Okay, like I said, highly conceptual. You might have to play around with that again, but this is super, super important. I can't stress it enough. Okay, talk to you later.